Okay, so we're going to start where we left off on Friday, okay? And I'm going to go through these example problems so you have some and we can complete our notes and not give you some like busy work assignment, okay? So we left off talking about the three integrated rate laws based off of the order, right? Whichever ones, when you graph them, if they give you a straight line, would determine if it was a zero or first order. So they're telling you, obviously, in this first problem, it is zero order, meaning if we plot the time versus the concentration, okay, we'd get a straight line, right? And I didn't spend the time doing the units, right? And because it's telling you it's a zero order. So plotting those two is going to give you a straight line. Okay, so if we flip this over, still using the same problem, okay, so since the concentration of N2O gives a straight line, it is a zero order reaction. Okay, so our integrated, remembering integrated is time dependent, would be the concentration of N2O equals negative K times time plus that initial concentration of N2O, whatever we started with. Okay. So we're going to get the rate, or our K, right, is the slope of the line. Okay, so I think we left off with this on Friday. So you can make a triangle on the graph and get the slope, or just plug into the integrated rate law. So I'm going to plug in at time 20. So I'm going to plug in at 20 seconds. That's what I'm going to do. So I want to find, using my integrated, I'm going to plug in at 20 seconds. That concentration is 0.0500 equals negative K. My time is 20 seconds plus the initial concentration. So if we flip back over and look at that chart, our initial concentration of N2O at time 0 was 0.0800. Okay, so we're going to solve for K, subtract our initial, yeah, 0.05 minus 0.08. Just going to give you negative 0.03 equals negative K times 20 seconds. So divide by 20. Actually, divide by negative 20. So we want the K. Okay, divided by negative 20 gives us, our K value is 0.0015 unity per second. Okay, so our integrated rate law, if we were to rewrite it, would be still concentration of N2O equals negative 0.0015 molarity per second times our time plus, right, the initial, which isn't changing, the initial concentration of N2O. So you can keep your 0.8 in there, 0.08 in there if you want, because it's not changing. Okay, remember your differential rate law is not time dependent, so it would be K times the concentration of N2O raised to the 0 power, which is just 1, right? So when we're solving this for a zero order reaction, our rate is in essence equal to our K constant, because this N2O raised to the 0 power, and that is equal to 1. So our rate is 0.0015 molarity per second. Would be our differential rate. I mean, it's equal, right? We wouldn't need that part of it. Okay, moving on. So if we, and I know this was a big question, or a lot, it was blank in a lot of your guys' stuff, okay, on your reading guide, and they walk through an example. So if we're trying to do half-life, which is going to come back, the last time we saw half-life, I think, was in general chem when you guys were doing nuclear equations. So half-life is the time for half of the reactant to be used up. Okay, remember our differential rate law is only for starting concentrations, and it is not time dependent, so we must use the integrated rate law when we're trying to determine half-life. Okay, so if we were trying to find our half-life time for our equation that we just had above, right, we're going to use the concentration of N2O equals our negative sign 0.0015 molarity per second times our time plus that initial concentration of N2O, which is 0.0800. All right, so there's our integrated rate law that we found above. Okay, so if we want to figure out our half-life, right, it'd be what half of this, we'd want to find the time when it is half of our original concentration. All right, so looking at this, right, half of 0.08 would be 0.0400. So we want to figure out what time would be when our concentration has decreased by half. Okay, so we're going to solve for our time. We got negative 0.04 times time. I'm going to divide both sides by 0.0015. So I'm going to rewrite this up here. So my time, half-life time, is that negative 0.0400 divided by negative 0.0015, which gives us 26.7 seconds. Right, and all we did there, right, to do this, you have to have found your K, which we did above, right? You look at your initial amount and you say, okay, I have 0.08. If I'm trying to find the half-life of that, what is half of that? It is 0.04, and then you solve for your time. So our half-life for this reaction would be 26.7 seconds. Okay, and once we find, right, once you know your integrated rate law with your K value, right, we can ask a ton of different questions. We can ask about half-life, right, or we can find certain concentrations after a particular amount of time. So this one is asking us to find the concentration of N2O at 50 seconds. So we're going to use our integrated rate, our integrated rate law equals negative K, and our K is 0.0015 molarity per second, times our time, which is 50 seconds, plus that initial concentration, which won't change for our integrated rate laws, 0.08. So we can plug in 0.08 So I get negative 0.075 plus 0.0800 equals, so my concentration after 50 seconds would be 0.0050 molar. And again, after we know our integrated rate law, we can find a lot of different things. So that was for 0 order. Okay, so we're going to jump. Now we're on page 11. We're going to look at problem 2 for a first order reaction. All right, so if we plot Ln of our concentration, we're changing it up to N2O5 versus time, and it gives us a straight line. So time, and your time can change in any unit. Most commonly you'll see seconds because the reactions are so quick. So we have our time in seconds and the Ln of our concentration of N2O5 gives us a straight line. Okay, so our integrated, right, gives us a straight line, is time dependent. So it'd be the Ln of our concentration of N2O5 equals negative slope, negative k times time, plus the Ln of N2O5, that initial concentration. Okay, and then our differential rate law, remember, is not time dependent, so it is the rate equals k times N2O5 raised to the first power. And they're giving us, okay, so remember, time dependent, not time dependent. And this is all based off of initial concentrations. This value will change, right? And our initial concentration in our integrated will not change. So find K when you start with, so we're going to find K when we start with 0.10 molar. And after 400 seconds, the concentration of N2O5 is 0.00625. Okay, so, and then it tells us, hint, use our differential rate law to find the units of K. Because it gets kind of tricky to use your integrated rate law to find our units for K. And we went through the trick, and I'll go through it again to find our units for K. So first, let's find what K is. Okay, we're going to use our integrated. So the Ln of our concentration of N2O5 equals negative k times time plus the Ln of N2O5, the initial concentration. Okay, so we're going to plug in. They're giving us values. Okay, they're saying we start with that, so that is going to be our initial. After 400 seconds would be our time, and after that time has passed, our concentration is decreased to 0.00625. So we're going to plug in Ln of 0.00625 equals negative k times 400 seconds plus the natural log of our initial concentration, which is 0.100. Okay, so if I plug in, you can do this all in your calculator. I'm going to actually write down what these values are. So when I plug in the Ln of 0.00625, I get negative 5.075 equals negative k times 400 seconds still, plus, and when I take the Ln of 0.1, I get negative 2.303. Right, so we're going to solve for k. Sorry, you can hear my daughter in the background. So I get negative 2.772 equals negative k times 400 divide by negative 400 divided by negative 400 gives us a k value of 0.00693. Seconds to the negative 1, and we'll talk about that. Or you can put it in scientific notation, 6.93 times 10 to the negative third seconds to the negative 1. Okay. And then how do we get those units? Okay, we know we're a first order, so it's nice to use your differential rate law. We know the rate is always molarity per second equals K. And if it's a first order, we have molarity raised to the first power, right? So what units would K have to be so that when you multiply the two, you get molarity over seconds? Well, it would have to be 1 over seconds, right? So 1 over seconds times the molarity would give you molarity per seconds, or, right, seconds to the negative 1. Okay, so we found our K values, so our integrated rate law would be ln of our concentration of N2O5 equals negative 6.93 times 10 to the negative third seconds to the negative 1 times time plus that initial concentration, the ln of the initial concentration of N2O5. And like I said, that value is never going to change. It's going to stay constant, so you can just plug in the value you want. So that would be our integrated rate law, right? And our differential rate law, remember, not time dependent, so it'd be rate equals our K, negative 6.93 times 10 to the negative third seconds to negative 1 times the concentration of N2O5 raised to the first power. Alright, so moving on, so if we were going to do half-life for our first order, again, the time for half the reactant to be used up, okay, our differential rate law is only for starting concentrations and has no time in it, so we're not using that. We need to use our integrated, okay? So we already calculated our K, we already have our integrated rate law equation right up there, right? We already found it. So use the K you calculated before to find the half-life. And they want us to find, kind of don't. They're telling us, right, or initially we had a 0.1 concentration, so what would half of that be? Half times that 0.1 would be 0.05. So if we plugged in, we have the ln of 0.05, right? Where did I get that? That's half of 0.1 equals at negative K, 6.93 times 10 to the negative third seconds to the negative 1 times time plus, right, the ln of 0.1. So we can start to solve, right, and rearrange. So I'm just going to plug it in, ln of 0.05 minus, because I'm trying to get this to the other side, minus the ln of 0.1 gives me negative 0.693 equals, right, negative 6.93 times 10 to the negative third divide so our half-life time would be 100. Be 100 seconds. Okay, so we can find our half-life time by just plugging in, right, what would our final concentration be based off of half of the initial amount. So, and then we just solve for our time. So we get time is 100 seconds. Right, our next question says, get the concentration of N2O5 after 10 minutes or 600 seconds. Right, so we'd have our ln times the concentration of N2O5 equals, and we can get to plug everything in, negative 6.93 times 10 to the negative third times our time, which is 600 seconds, plus the ln of our initial concentration, which was 0.1. So you plug everything in your calculator. So I get negative 6.93, second E, negative 3, times 600, plus the ln of 0.1. So when I do that, I get the ln of N2O5 equals negative 8.763. Hey, so remember we talked about this last week. How would you get just the concentration of N2O5? Right, we'd raise both sides to the e power. So keep that number in your calculator, right, and then that goes away. So we end up the concentration of N2O5 equals e raised to that. So I'm just going to plug in, keep it in my calculator, e to the answer, and I get my concentration after 600 seconds would be, should have put this in scientific notation, 30156. All right, and then our last one on this one is get the rate if N2O5 0.560 is made. So get the reaction rate, which means we're using our differential rate law. So rate equals our negative K right, and we're dealing with an initial concentration of 0.560 raised to the first power. So our rate would equal, we don't need the negative sign there, our equation, 0.00388, oops, all right, 3.88 times 10 to the negative 3. And remember, rate is always molarity per second. You can't see that. Okay, and the reason I got rid of that negative sign, because it is not, right, that negative is in your integrated rate law. It's the negative K, and for our rate, it's just our K value, so we wouldn't need that negative sign there. All right, last one. I will skip, try and, right, make sure you guys aren't asleep. Okay, we know, right, if we plot 1 over the concentration, right, and it gives you a straight line, then it is a second order, right? So our integrated rate law would be 1 over our concentration. It's a positive slope, so K times time plus 1 over the initial concentration. Right, differential rate law is not time dependent, so rate equals K times the concentration raised to the second power. Okay, so what you can do here, right, we can solve for K. They're telling you if we start with, so there's our initial concentration. After 6,200 seconds, we have our concentration is 0.00208. So we can plug in to find our integrated rate law. So 1 over 0.00208 equals my K after 6,200 seconds plus 1 over 0.01. And I get this over there. So I'm going to do it all at one time. 1 divided by 0.00208 minus 1 over 0.01. And I take that over, I get 380.8 equals K times 6,200. Divide both sides by 6,200. So my K equals 0.0614, right? And it is a second order, so molarity to the -1, seconds to the -1. Okay, and again, where would I get those units? Remember, rate is molarity over seconds equals my K, and this is a second order reaction, so I have molarity squared. So molarity squared times what is still going to give me molarity over seconds, right? So what would this have to be here? Well, you'd have to have 1 over molarity times seconds. And then that one would go away and you'd be left with one of those. Okay, so there's our K. So our integrated rate law is 1 over our concentration of C2H of C4H6 equals, it's positive 0.0614 times our time plus 1 over the initial concentration of C4H6. Okay, second order reaction, so our differential rate law would be rate equals 0.0614, again, molarity, second, -1 times the concentration of C4H6 raised to the second power, because it is a second order reaction. All right, last example, now you have an example for everything, for each one. Okay, if we want to find the half-life, we're going to use our integrated, we have our K, and if our initial amount, which they told you was 0.01, right, half of our initial amount, so that initial amount, and I got that from above when we found K, our initial amount was 0.01. Half of that would be 0.005. Okay, so those are two values we're going to plug in to find our time. So I have 1 over 0.005 equals 0.06142 times my time, or you can just have 0.0614 plus 1 over 0.01, that initial amount. So I do this, I get 1 divided by 0.005, that's 200, minus 1 divided by 0.01. So I get, when I take this over, and so I get 100 equals 0.0614 times my time, so I'm going to divide both sides. So my half-life time, 100 divided by 0.0614, gives me 1,628 seconds. So half the time. All right, find the time for 25% of your C4H6 to be gone. Okay, So it's really tricky to think about, like, what do they mean by that when you're plugging in, okay? So you want 25% to be gone, but when we're plugging into our equation, we're plugging in what's left. So really what we're looking for is what is the concentration when 75% remains? Okay, so we would take our 0.75 and times it by our initial concentration, which was 0.01, which would give us 0.0075. Okay, so this would be the value you're going to plug into your equation, and you're going to figure out how much time it takes. Okay, because it says find the time for 25% of that to be gone. Well, when you're plugging in, you're not plugging in 25% is gone, right? We're plugging in what's still remaining in our equation. Okay, so we'd plug in, I'm going to change colors so we can kind of see where we're at. So my 1 over 0.0075 equals 0.0614 times time plus 1 over 0.01. All right, and we'd find our time there. Okay, and then you can plug in, right, figure out the concentration after 1 hour, 3,600 seconds, okay, using your integrated. And then this last one, the reaction rate, you would not be using your integrated. It is not time dependent, so we'd be using rate equals RK value that you have times the concentration is C4H6 raised to the second power, based off of the initial concentration they're giving you. Okay, so here's an example of each of them. You've now completed your notes. Okay, so I'm going to give you guys some practice problems to work on the rest of the period. And if you have any questions or concerns, come see me tomorrow, Wednesday, at lunchtime. I will be here. All right, thanks.